I'm Brian Browning. I'm at the University of Washington. I work predominantly on methods development, mainly in the space of methods that work with haplotypic data, haplotype data, which if you don't work in that space, there's actually a lot of downstream methods where haplotypes are the beginning, the input to them. And so that's why I'm focusing on phase sequence data. You essentially get the unphased data comes along for the ride, but you get the phasing too, so it's a very versatile form of data. And with biobanks, it's getting challenging to work with. Let's see, where's the next? So if you're not familiar with what phasing is, just two brief review slides. The data that we usually see in most cases is we see at each different sites along a chromosome the two alleles that you've inherited, one from the mother, one from the father. And that's what's shown up on, actually let me go up a line. That's what's shown here where the line represents the chromosome. You have the two alleles, but what we don't usually see, and most of the data out there we don't see, is how those alleles were inherited as sequences from the parents. And that's what phasing tries to get at. And if you have large sample sizes, we usually use statistics to phase, statistical methods, and they actually are very accurate for large sample sizes. And we make an inference that's almost as accurate as the underlying genotypes of what the alleles are on each, that were inherited from each parent. So if you look here at each site, you see you still have the same pairs of alleles at the bottom. The first site's AG, the last site is GT, still the same. But now you have that second dimension where you can see how they're transmitted as a sequence from the parent. Now, the way genetics works and the way information gets passed down is people share stretches of haplotypes, stretched sequences of alleles. And that shared sequence, the shared sequences that are out there in a data set give great potential for compression, as you'll see when I'll give some raw data at the end of the talk where you can get a sense of how much this type of data can be compressed and what's the nightmare it would be if we couldn't compress it. So most haplotypic-based methods work with something called VCF format, variant call format. This is just a quick slide of review. If people have not seen it or you're working in a different space, starts out with some header lines with double hashes. There can be thousands of these lines if you have a line per contig or something like that. There can be a lot, but they don't take much space up. I'm not worried about those. The next type of line is the sample line that has a hash and starts with chrome. These essentially give column identifiers for everything that follows. The first 8 identifiers give you information about the site. They give you site level information. So you get the chromosome in the first column, the position in the next. Here the ID is missing data, but if you have a SNP identifier, you could throw it in that third column. You get the reference allele. You get the alternative alleles. One or if there's more than one, you can have more than one. You have a measure of the quality, then some information whether if for sequence data in particular, if it passed the filters or if it failed, which filter it failed, some kind of code. And those first 8 columns are that's not where most of the space comes in the file. They're just giving site level information. Where it gets expensive in terms of storage is once you start giving the per sample data. So the format column tells you what kind of data you have for each sample. And here we just have a GT code because that's what I'm focused on compressing. You can store other per genotype level data, like the alleles, the number of alleles that support, number of sequence reads that support each allele. You could store that. Then this becomes much less compressible. But if you're just storing the genotypes, we'll see that we can compress fairly well. And for most downstream analysis, that's what you need. If you have QC information in the info column that you can have a number of marker level QC metrics that summarize the quality of the sequence reads. That's usually for mini analysis good enough for your filtering. And then you just have the genotypes. For most analysis, that's what you need. But if you, in the small case, subset of cases where you need that other information in the per sample, I'm not going to deal with that. There are people who've worked on methods for this. It's a much harder compressibility problem. You won't be able to get nearly the compression that you're going to see in this talk. So now that we have large-scale data sets, the sample identifiers here, which I'm just saying ID1 and ID2 on the sample line, normally you'd put your sample identifier from your data set. You could have a million, well, we're not up to a million data sets at least that we regularly work with in academia, but we're up to 500,000 now. So that's, 500,000 samples, that's 1 million alleles, going out. So you have a very wide file. And if you're dealing with a large, set of 500,000 individuals, a large chromosome could have 100 million lines. So essentially you have this huge matrix, 100 million rows, a million columns, more than 1 million columns, and that's unwieldy to work with. And this is sort of the fault of all the huge strides they've made in sequencing, right? It was a big deal when we reached the $1,000 genome. Well, now we're starting to approach the $100 genome. When it gets that cheap, you can sequence a lot of individuals. So the All of Us project, the goal that I've seen in their releases is they're looking at sequencing 1 million individuals. My guess is it'll go higher. I haven't seen projections for higher, but it's hard for me to imagine they're going to stop there. Our Future Health in the UK seems like it's quite far along. They're looking at collecting 5 million samples. If those are sequenced, that's going to be a big data set. 5 million genomes, my back of the envelope calculation, if you're uncompressed, in VCF files, you're looking at 15 petabytes, right? So it's, kilo, mega, giga, tera, peta. So it's, we're often working on the gigabyte scale for maybe large files. Well, now you're jumping a couple up into the peta scale. If you gzip compress, it turns out gzip, because of the nature of sequence data and the way gzip works, you can get about a 300-fold reduction down to 80 terabytes. Still, if you haven't worked with that file size of data, and when the first time you do, you will not enjoy it. It's just really frustrating to work with. Now, this is a methods talk, so everything going into this talk is sort of related to a method I'm going to present. On Friday, there'll be a tutorial talk where it'll fill in a lot of the bigger picture. So in the tutorial talk, we'll talk about gzip, how it works, why it's so effective on this data. I mean, it's not as effective as we need it to be, but it's still pretty impressive to squash it down by a factor of 300. Why is that? We'll talk about that on Friday. So this is not the method I'm presenting, but it's a building block in the method I'm presenting. So I want to talk about something called M3 VCF, which if you haven't worked with imputation, you may never have heard of. But it's a compression method that was designed for reference files when you're imputing ungenotyped markers. So it's the situation where you have some sequence data that's phased on a large number of individuals. You have some SNP array data typically, where you just have maybe 500,000 sites genotyped, and you use the reference panel data to impute the ungenotyped markers in your SNP array data. So it's a very cheap way of turning SNP array data that is legacy data typically from the last 15, 20 years into sequence data. It's not as accurate as high coverage sequence data, but it's good enough for many types of analyses. And it's surprisingly accurate. All right, so M3 VCF, the idea is simple. I like simple ideas and methods. You partition the chromosome into windows, and for each window you store the unique allele sequences, and then just a pointer that goes from the haplotype to the allele sequence it carries. Idea is very straightforward. It may not, if it's not clear from the text, I think it'll be from the picture. So hopefully people can see this, it's not too low, but we've got, on the left-hand side, we've got some color-coded haplotypes. So this is a toy example, 6 haplotypes, those are the rows, and we have 47 markers in this window. That's just, again, this is just a toy example. And if you can make out the colors, haplotypes 1, 5, and 6 are colored in green. That indicates on this short window they have the same allele sequences. 2 and 4 are orange. They have the same allele sequences. H3 is in pink. It's the only one with coded pink. So you have its allele sequence is only carried by itself. So how do you compress this using this M3 VCF approach? Well, you just store the unique allele sequences. So that's 3, the green, the orange, and the pink haplotypes. That's on the right side of the screen. And then you just store a pointer, just one machine word that point, or you can even do it, there's ways to even compress it further, but some kind of pointer pointing from the haplotype to the sequence it carries, which I've notated here just by a colored box. H1 carries the green haplotype. H2 pointer says it carries the orange haplotype. this is lossless. You haven't lost anything, and you can see the compression from the arithmetic on the bottom. Here you got a matrix of 6 times 47. Here you have a matrix of 3 times 47, so that's where the savings is. You have to pay up the price of the pointers, storing the pointers. But in general, it compresses. And it turns out, in this toy example, you can't see how well it compresses, but it turns out that it actually compresses better than gzip, which it already does a pretty good job. So then a closely related compression method called Bref4. This is something that my software, Beagle, uses for imputations for a similar purpose. And it's very similar, it's just it handles low frequency markers different. So sequence data has lots and lots of low frequency markers. Often, around half the markers in your sequence data, there'll just be one copy of the minor allele among all your samples. Right? So, 99.99% of the alleles are the major allele, and there's this one outlying minor allele. So what it does is it just stores the indices of the haplotypes carrying the minor allele. So if haplotypes 52 and 998 carry the minor allele, you store two numbers, 52 and 998. It's lossless. You ask me what allele is carried by haplotype 70. Well, you look in your list, does the list contain 70? No, so it has to be the major allele. What haplotypes carried by haplotype, the 52nd haplotype? You look at your list, 52 is in the list. It carries the minor allele, so it's lossless. You just look, whether a haplotype index is in the list, and the answer to that question tells you whether it's a major or a minor allele. And you can see the compression here, right? You have a million alleles. You could store those million alleles, or you can, if there's only 2 copies of the minor allele, you can store 2 numbers. Huge compression. And that's very effective on sequence data because there's so many low frequency markers in sequence data. Now, once you've peeled off those minor alleles, you're back to the same scenario as M3VCF. You partition the remaining high frequency markers into windows, store the unique allele sequences on each window, and 1 pointer per haplotype. So when you're doing this type of approach, like when I checked recently, M3VCF and Bref4 have very similar compression, amounts of compression on the test data set I looked up, which is what you expect. They have the same basic conceptual framework, although they differ in how the windows are defined. And setting the window lengths isn't super obvious. Oops, just a second. Setting the window lengths is not super obvious. So can you make the windows too long? That saves you from having to have a lot of windows, which means you have to store a lot of pointers. Well, if you make the windows too long, all your sequences are unique. Even if you think, wait, well, what if there's a monozygotic twin in my data set? They won't be unique. Well, genotype error, yeah, they're going to be unique. Genotype error, even if the sequences are the same, the data you see, they won't be the same. And so you end up storing, when you store the unique allele sequences, you're storing them all. You're getting no compression, and you then have to pay the price of storing the pointers. So no, that's a loss. You could make the sequences shorter. So here, down to the other extreme, we go down to 1 marker. Well, this is just a 1 marker haplotype. That's just alleles, right? You have a green allele and an orange allele. And so the unique allele sequences, there's just 2, the green and the orange allele. But the pointers, if you think about it, you're just recapitulating the alleles over here. Your pointers are essentially telling you what alleles you have, and so you aren't saving anything on the short if you make things too short either. So unfortunately, you just can't say longer is better, shorter is better. It's not. This is just a made-up quadratic graph. I mean, I don't have actual data underlying this, but this is what you expect to see intuitively, that too short's not good, too long's not good, and there's some kind of sweet spot in the middle that would be better. And how you choose that's not super obvious. I'm going to give you a heuristic that I like it because conceptually it's simple, and it's tunable, and it should give you something close to optimal. So what you can do is just set your window length based on the number of unique allele sequences. So H is the number of haplotypes, P is some proportion, in one of my projects, I tuned this to be about 0.25, a quarter. And the idea is you just start marching along. You go one window or one marker, and you have the number of alleles. You take the next marker, you have a few more unique haplotypes. Every time you add a marker, the number of unique haplotypes can go up. It can't go down. It can only stay the same or go up. You just keep marching along until the number of unique sequences is p times h, or close to it. As soon as it is, you stop, you start the new window. So conceptually, that's a very easy way to define windows. I mean, the downside is that it's tough to parallelize. It's a very sequential algorithm. But other than that, conceptually, it's very straightforward. And you can tune the p for your type of data to see what works well. And then once you have the windows, you look at the unique allele sequences and you store them and get the map from haplotype to allele sequence, the pointer. I want to back up. I sort of skipped through one slide I wanted to talk about. So these methods that we talked about that are very closely related, M3 VCF and Bref4, they have a really nice property, at least I find when I work with these type of data. You can analyze them without decompression. You can just read them in as they are into memory. In M3 VCF's case, you have to do some parsing from text to binary. Bref4, you don't even have to parse. You just read them into memory, and you can work with it straight because you can put an interface around them to make it feel like you're just working with a matrix, which is what you want. So here's some pseudocode. You have allele, you have Bref4 data. I want to get the allele at this marker and that haplotype. It feels like you're interrogating a matrix entry. Marker's the row, haplotype's the column. The value is going to be the allele carried on that marker, on that haplotype at that marker. It feels just like an array. You're doing a matrix query. But because it's an interface, you don't really see what's going on behind the scenes. You can have this as sort of a wrapper or an interface to your Bref4 data or your M3 VCF data. What's the difference? Well, if you really, underneath it really was stored as a two-dimensional array, you'd have two array lookups. An array lookup to get to the row, and then an array lookup to get the allele on the column. Here, with Bref4 data or M3 VCF, it's typically three lookups. A lookup, you get from the marker to find the window. From the window, then you look to find the unique allele sequence carried by the haplotype in the window, and then a third one to get the allele that's at that marker. So it's just a little bit more, and it's not clear that the performance will be much worse because you should have fewer cache misses with the compressed data. With Bref4 format, it's also possible for that marker to be low frequency, in which case, again, this is the beauty of having an interface. You don't see what's going on behind the scenes, but behind the scenes, all it has to do is then do a binary search to find out whether the haplotype you're asking for is in the list of minor allele carriers for that marker. Right? And that's, since these are rare variants we're talking about, the array that it's searching is very small. It's a very fast lookup. So that is the great thing about these compression methods is you can treat them as if they're uncompressed data when in all your code working with them, but underneath, behind that interface, you get compressed. So you can use smaller machines. You can analyze whole chromosomes worth of data where if you didn't have it compressed, you wouldn't be able to fit it on any kind of standard machine. There'd just be too much data. How much compression do you get? Well, we'll have some data at the very end of the talk. It's better than gzip files. It's good. But it's worse than something called the positional Burrows-Wheeler transform, PBWT, with run length encoding. It's worse than that. So what I'll want to show you later is we'll look at a method that hopefully can give us both things, the best of both worlds, that we can analyze without decompression, and we can get that little bit extra compression that the state-of-the-art methods have. And it turns out, and I won't dwell on this today, but on Friday I'll talk about some properties that this new method I'm talking about has, and it's also shared by these other methods that PBWT does not have. It turns out you can do more things with the data in compressed state than you can with the positional Burrows-Wheeler transform. With the PBWT, most of the time you're going to have to decompress it to work with it. And that's expensive, and it blows up things in your memory, in your computer memory when you're analyzing. So this method I want to talk about is Bref4. It's going to build on these other methods. And it starts out the same as Bref3. First, didn't even mention it on the slides. You take the low frequency markers and just store the haplotypes indices for haplotypes that carry the minor allele, and you just store those. That gives you very good compression on the low frequency. So from here on out, we're going to pretend like all the markers exist are high frequency. And the first step's just like Bref3. You take the high frequency markers, you divide them into windows, and I gave you an algorithm, a heuristic, for how to divide into windows by looking at the number of unique allele sequences you have for determining when to end one window and start the next. And so here we are. We're right at this point. If we store that, we'd be in Bref3 land. But we can do more. So what happens here is this is a window. What happens if we consider this window to be a whole chromosome and consider these to be the haplotypes carried on that chromosome? We could repeat this. Just do the same thing again. So we can divide that window into subwindows. Now, the haplotypes are unique at the window level, but on the subwindow level, we expect, though by the way we constructed our subwindows, we'll have duplicates. So we have duplicate allele sequences on each of those, in this toy example, each of those 3 subwindows. And we can use the fact that there's duplicates to apply in 3VCF, or similarly, Bref3 compression again. You just store only the unique haplotypes and then store a pointer from these 4 unique haplotypes observed in the window to the haplotypes, or to the allele sequences carried on the subwindow. And you just continue this process. So it's sort of the same idea, but we're going to do it again. And we're going to do it again. Each time you take a window, you break it into subwindows, and you get compression on each subwindows. The subwindow that you had from the previous iteration now becomes the window. You break it into subwindows, and you just repeat. And at some point, you have to stop. We stop when the subwindows have, when you get to a point where there's less than 16 unique sequences in the subwindow, we stop. Okay. So in a sense, this is a way of solving that problem of what's the optimal window length. You just have big window lengths where you're not storing many pointers because there's only one window, so you only have to store pointers for one window. Do you have small window lengths where you have lots of windows, so lots of pointers, but there's more duplicate allele sequences because you have a small window? And if you've seen things like cache oblivious, what is it? Cache oblivious algorithms, it feels to me like it has a little of that flavor. By using this recursive strategy, we're essentially handling the case where we don't really know what the most optimal window size is. So how does it perform? This is on UK Biobank 200K sequence data. And we looked at different subset sizes and just looked at the size we got from using a gzipped VCF file, which is pretty good compared to uncompressed VCF. And then looked at Bref4. And interestingly enough, for this data, as we just kept increasing the sample size, there's a very consistent growth pattern. The gzipped VCF file, when you doubled the sample size, doubled in size. But the Bref4 file only went up by 60% in sample size. So that's why you get this huge chasm opening up in file sizes. And when on some data I've looked at, Bref4 is very similar to PBWT in compression, unless you then follow up PBWT compression with gzip compression. If you do that, you can get a little bit lower, but then you've got another layer you have to unwind to work with. There's some disadvantages to doing that, and it's not much of an advantage. You're not getting much extra compression. Here's some data from all of us. This isn't out there yet, but I think it's scheduled to come out later this year. 412,000 individuals. Looking at a 10 megabase region, then I took the file sizes, multiplied by 300 to get up to 3 gigabyte 3 gigabases to approximate what kind of file size we need to store the entire all of us data, the version 8 data that's not yet out there, but the entire all of us data in this format. So the uncompressed VCF is 1.2 petabytes because these are in gigabases in the second column. So that's tough. Gzipped VCF gets it down to 3 terabytes, 3.6 terabytes rather than petabytes. So you get 99.7% compression. Very, very good. But terabytes files, yeah, it'll fit on a thumb drive, but if you've ever tried to copy files that approach 1 terabyte in size, or work with them or process them, it's slow and it's not fun. Bref4, if you look at the diagonal entries, they give you sort of the improvement on the preceding line. Bref4 drops it by another factor of 9, which is pretty respectable. Especially when you think that unlike gzipped VCF, gzipped you have to decompress to work with. Bref4 or M3 VCF, you can work it in memory essentially as is, in compressed state. So that's not only to get a smaller file size, but you can work with it directly. And then Bref4 gets it from about 433 gigabytes down to 86 gigabytes. 500,000 people, genome-wide sequence data. And it gets essentially another 5-fold compression. So it looks to me like, at least the foreseeable future, it is possible to continue to work conceptually with VCF data, although life's much simpler, if you use one of these sort of things that's designed to be a lossless form, compressed form of VCF data. But it does work well. Let me just finish with a summary. So we try to design a method that it reaches two goals that often are in conflict. You can have excellent compression, but because things are compressed so much, trying to get data out of it, you can't. You have to decompress to use it. And things that's more analysis optimized. Analysis can be formed in the compressed data, but because you're designing it so you can analyze it directly, you can't squeeze all the space out of it. You can't try to optimize the compression. So this comes very close to giving you both things. You can get the good compression and still analyze it with one caveat. Because of this, each window is being broken up into sub-windows, is being broken up into sub-windows, and that iterative process, you've got to access an allele, you've got a lot of array lookups, array queries, because every time you go from a window to a sub-window, you add an array. It's like you're have to look up and retrieve a value from an array, and that gets expensive. So and this is an unusual case, you only need to look up a few alleles here or there, you can just work with things directly in Bref format. But if you actually want to do analysis on it, some kind of haplotype-based analysis, maybe local ancestry inference or IBD segment detection, it's not really practical. But there's a simple workaround. And this is, I don't know if I've seen this elsewhere, although it's a big world. I'm sure somebody else has done something similar. It's the idea of partial decompression. Most compression methods, it's like, you compress it all the way, and when you work with it, you decompress it all the way. You might have choices of tuning how much the compression happens, but it's either all in, all out. Bref4, by the way it's constructed, you can, as you're partially decompress it and arrive at Bref3 format. And we know that we can work with in memory, and it gives us, it's not as good a compression as Bref4, but it's, within a factor of 5. So you do have to pay the price of decompressing, but compression costs a lot more than decompression generally, right? Trying to figure out how to compress something usually takes a lot more time than decompression. And second, we have some slush money, computational slush capability, because we're reading in a file that's 5 times smaller than Bref4. So you're saving on file reading time, but you may have to pay a little bit back, which usually, the internal computations are faster than reading from a file, but you'll pay a little bit back to partially inflate up to Bref4 format, and then you can use. So there is a workaround that we use, we've sort of built into our methods, and it seems to work very well. So that's the last thing here. There'll be a tutorial talk on Friday that will talk more about gzip compression. If you haven't seen the positional Burrows-Wheeler transform, we will talk about that and how things are compressed with that. If you haven't seen the PBWT, I highly recommend it. It's something you should be at least familiar with and have in your toolbox. It's really a cool tool for bioinformatics. Any questions? Yeah.